In the fourth episode of Baya's Tech Threads podcast, we welcome Rochan Sankar, founder and CEO of Enfabrica, a rapidly growing startup with backing from industry giants like NVIDIA and ARM that is bringing disruptive networking technology for the next generation of AI to completely remove clutter and scale fast to clusters of up to 500,000 GPUs.
Welcome to Tech Threads, Weaving the Intelligent Future, the podcast exploring the fast-paced world of technology. In each episode, we dive into the latest innovations in data movement, AI acceleration, and the transformative potential of chiplet technology. Join us as we explore the breakthroughs that shape the future of computing and hear from industry experts on what's coming next in the tech landscape.
Hello, and welcome to the fourth episode of Baya's Tech Threads podcast. I'm Nandan Nayampally, Chief Commercial Officer at Baya, and today I'm thrilled to welcome another rising star, Rochan Sankar, founder, president, and CEO of Enfabrica, a company that's revolutionizing AI infrastructure and networking. Enfabrica is tackling one of AI's biggest challenges, the networking bottleneck. Their accelerated compute fabric, SuperNIC, breaks through current scalability barriers, enabling AI clusters of up to 500,000 GPUs, up to 5 times the current industry standard. Last year, Enfabrica raised $115 million in its Series C round, backed by investors including NVIDIA, Cisco, and ARM, and Enfabrica is really positioned at the cutting edge of AI infrastructure. As for Rochan himself, before founding Enfabrica, he was the senior director at Broadcom, where he led their data center Ethernet switching business, defining and bringing to market 4 generations of groundbreaking chips that drove cloud networking innovation. Welcome, Rochan.
Hi, Nandan. Glad to be here.
Great. And before we jump into the main discussion, I firstly wanted to congratulate you on the delivery of your ACF SuperNIC to your customers. Do you want to tell us a little bit more about it?
Sure. It's significant excitement over here in the past few months. As you know, startups are a labor of love, and we've been at this for several years, building the silicon, the ACF SuperNIC, with really a vision towards how it can accelerate and make significantly more efficient data movement inside of AI and accelerated computing clusters. So we've been at this for a while, and we successfully taped out the chip last year, in the late part of last year, and silicon came back earlier this year, and it's working swimmingly in the lab. We're passing trillions of packets through. We're saturating the line rate of wires. We've validated the data paths of our NIC and switching functionality, and we've shipped to customers. So it's a great moment for us to see our vision for how a refactored and new product in this space can add value to how customers are building out their AI infrastructure. And we're happy to see it get out there and start to proliferate in our customer environments.
That sounds awesome. And in fact, there was a lot of discussion online about 1, the line rates, and 2, trillions of transactions lost less. So congratulations.
Thank you. It's a result of a lot of hard work of our great engineers.
Speaking of your first statement there, startups are a labor of love. We understand that. Clearly, you've been through a lot of labor over the last few years. Tell us a little bit about your journey. You obviously were doing great at Broadcom. Broadcom is still going from strength to strength. So what was your motivation for building Enfabrica?
Yeah, I think of this space overall as being something that's extremely intellectually stimulating, right? To be able to build products that actually are part of the hardware foundation by which programmers, consumers all increase their productivity, or we're able to advance the state of the art in science or technology, and that's a great thing to be a part of. And there are advantages to doing that in a big company and in a a highly regarded world leader or industry leader like Broadcom, or at a company like NVIDIA or the like. But when you have an itch, you kind of have to scratch it. And then that itch a few years ago was that if you can see some things around the bend, and you believe that you can build, and you can build more capable product or systems or, teams than what you currently see around you. It's that itch is hard to resist, to scratch. And that's where we found ourselves, myself and my co-founder, 4 or 5 years ago, especially with this huge market opportunity and technology opportunity with AI and how that could seriously be seen even at that time, because this is all before ChatGPT and the like, of being a massively impactful transition for everyone and for the entire industry. So, starting on that and actually having the, being able to hold your breath and having the energy and motivation to kind of say, okay, let's go try and build something. And, there's always the risk of failure around every corner. And you just have to feel compelled in some way that you're willing to do that and willing to learn from it. I think that's the biggest thing. The biggest opportunity here was to really learn how to build something and how to build something at scale and do it in a way that actually delivers tremendous value to customers, which we're still in the journey of doing. But, we're always getting halfway there. Every single step is getting halfway there. So eventually we'll close in on where we want to be.
No, that sounds great. Now, let me kind of dwell on that for a little bit, right? So there's two reasons to go build a startup. One is I'm going to do something very different, or where I am is not moving in the direction I think it should, etc. Or two, of course, but the sheer either challenge and the potential upside of building a startup, right? So I'm sure there's a bit of both, but can you give us a little bit about how you felt? And if so, what are the challenges that you think of from a new semiconductor startup, which is a non-trivial exercise? How did you go about it?
Yeah, that's, it is equal parts, or at least, there's elements of both that factor into, the motivation to do this. And by the way, it can't be, a spur of the moment motivation. I mean, this is painful, long, arduous work to try and get this doing. So you really have to feel like there's, not just motivation to do it, but sustaining energy, support, from your team, your investors, the market, customers, to be able to go do that.
In fact, Jensen's kind of famous for saying if he knew how much pain there was, he wouldn't do it again.
Yeah, but, I think that's his way of discouraging the rest of us from doing it.
Sorry, I interrupted. Please go ahead.
But in terms of, there are really two factors, right? There is obviously incumbency and the way that things are being built, and you have to see an opportunity for disruption, right?
Yeah.
In many ways, you could see it as like, hey, I wish we could build things this way. And, large company constraints sometimes prevent risk-taking, really, in terms of being able to fund and really take a chance on a vision of, like I said, seeing around the bend. There are some companies that do that. Companies like Google fund kind of like moonshot type of projects and the like. But I think in the semiconductor space, there's a lot of incrementalism, right? Think about it. A lot of people look at the product cycles and think, okay, well, it should take you about 2 years to build a new chip. Well, the reality is every new chip is like 85% an old chip. It's built on primarily the code base and the way that was built and the architecture and the frameworks that have been built over maybe, 10 years, 15 years. We have products that are on like, the 6th generation, because you can tell by their product name, product name number 6 or number 5 or number 8, right? Like it's very commonplace. So that means that by definition, it's incremental. It's really not necessarily disruptive to how, the fundamental problem is being solved. So we saw that opportunity in networking because all of networking components, whether you're looking at NICs or switches or the like, were built for CPU-based data center workloads.
Mm-hmm.
Okay, there's no disputing that, right? All of the ways that NICs and switches and PCIe level bridges were built were not built for AI. They were built for an era of more serial x86-based computing. But now when you see this completely parallel computing paradigm starting to take hold, which happened, certainly even in the early, 2020, 2021 timeframe with recommendation engines, and then you had LLMs explode onto the scene, in 2022 and beyond. There you see a huge opportunity to redefine just what is the most efficient way to move data. We were able to adapt what we had started working on in 2020 to, the realities on the ground and the problems that and pain points that customers were experiencing and still experience to this day. And that gave us the motivation. I mean, that was the motivation to go continue to build this out relative to, maybe what the status quo was, right? So that was part of the equation. The other part of the equation was that, from a standpoint of building something that that had a chance to succeed, that you could learn from, that was an opportunity to just do something new and different. That is definitely, a way of sort of saying, there's a different way to build things, right, than what I've used to seeing. And, part of that is experimenting, right? In being willing to fail and to be able to find the combinations of, collaborative practices, R&D methodology, the way that you come up with an architecture or validate it, the speed with which you make trade-offs in features versus schedule versus functionality. When you, have an inkling that you can build a product, faster, more capable, you want to be able to try that out versus your previous constraints in learning. And I think that that's something that if you feel it, compelled that you have an idea to do that, it's worth pursuing, whether it's in your own sandbox at a big company or, by trying it in an organization of your own.
Cool. Yeah, I mean, I think I have the good fortune of being in startups, especially IP startups, initially Denali, which is now Cadence, and then 16 years at ARM. And I've seen, had the luxury, I would say, and the good fortune of seeing how startups operate, how big companies operate. And yes, you can tell the difference, right? And that also kind of puts me back into a startup and Baya, which is trying to do things differently, having done a couple of things the first time around, second time around, and now taking another kind of swing at it, as you say, looking around the bend. Speaking of which, right, both of our companies are focused around data movement being a challenge that needs to be solved for the next generation of AI, but for all forms of compute. We think of compute as widgets, but it's really now it's about the data moving between those widgets efficiently is what matters. Now, we kind of operate at angstrom and nanometer level on die, and to some extent at maybe millimeter level between die. But clearly, data movement is at microns, it's at nanometers, it's at millimeters, it's at meters, it's at kilometers. So do you want us to kind of walk us through some of the levels and how we kind of discuss that a little bit further?
Yeah. By the way, I admire what you guys are doing over at Baya. I think the problem that you're, I obviously resonate with the idea that data movement is core to the AI problem, and there are different scales to solve that. And you guys are disrupting the way that network on chip interconnect and die to die interconnect has been done historically, and how it should be done going forward. I applaud you guys for attacking that space. We're doing the same kind of disruption, but we are doing it at the level of chip to chip within the system, and then scaling out the system to large scale clusters. The reality is what AI and accelerated computing has created is the data center scale server, right? The computer is the size of a massive, thousands or tens of thousands of nodes, all working together, highly choreographed between their compute operations, their communication, and data exchange operations, in order to come up with a massive supercomputer that's either training or inferring, models at scale. That's basically the problem statement. So it requires the most efficient data movement at all the layers, right? The most amount of the time that you spend where compute is idling is wasted time, right? And leads to a loss of efficiency or utilization of your capex. So I think that in the first, kind of race towards the deployment of solutions to satisfy the need for these large scale models, we've sacrificed some efficiency. There's definitely been sort of a more brute force way of doing that with respect to how current systems are built. Low levels of utilization on the GPU, not full utilization of the bandwidths being allocated, bottlenecks themselves in the memory bandwidth versus the flops versus the network interconnect. These are all three resources that have to be strike an optimal and programmatic balance, in order to satisfy what the workload needs are. So the way we see Enfabrica solving this problem is really elasticizing the scale up versus the scale out domains, how big you want to be able to do parallel data delivery to all of your compute resources or data store resources within a rack or a system, and also scaling that out. And we looked at the NIC, the network interface controller, as being the device that could have done this historically, but never did, as now being the point in the system where you can actually elasticize the communication in both directions, in the scale up dimension and the scale out dimension. And that solves a major problem. It's also the only thing that we're competent at, which is data movement, right? We're not here building new GPUs or ways of crunching the data, but we are extremely competent at trying to move the data and choreographing the hardware and software stack in order to make that as efficient as possible.
And in fact, part of your pitch is about some level of aggregation into this super NIC, and at the same time reducing clutter as you kind of think across scaling functions. Do you want to touch on that a bit?
Sure. So I would say that it comes down to three dimensions of performance. The first is that we believe that a NIC should be a multi-ported device that can actually act as the first hop of the network. And the reason for that is you want path diversity into and out of the node. You want to be able to spread traffic and be able to connect it to as many pathways as possible. You can think of it as like, the same way, your circulatory system works, right? You want to be able to have like a bunch of distribution layers to be able to get to anywhere where you want to go, depending on whether it's like, disruptions or interruptions there. And so we believe that that is core for both performance as well as for resiliency, right? To be able to, because resiliency of these systems, when you talk about a data center scale computer, one major fault there in a parallel workload can actually adversely affect or bring down a pretty large radius of the workload. So that's one aspect, is that just network level connectivity needs to be diverse, needs to be resilient, needs to be multi-ported. The other thing is basically, the other area that we focus on is scalability. So the way that we move data should be able to scale to, as much as possible within a node, with as much as low latency as possible, and as high throughput as possible across a very wide scale, right? Tens of thousands, hundreds of thousands of nodes. And to do that, you need a pretty well thought out architecture of how your data movement actually works in silica. Meaning, you put items into work queues, and then those work queues have minimal amount of touch in terms of trying to get that data to its next hop and beyond that, to be able to scale, again, in both dimensions. You can measure these things at the level of throughputs and latencies, but ultimately you measure it at scale. You measure it when you could basically say that a workload is undeterred in being able to move data from point A to point B at a certain amount of throughput, transfer megabytes or gigabytes of data from a producer to a consumer, and to modulate the hardware protocols and methods that you communicate under the hood, but keep it relatively transparent from the programmer. So the programmer shouldn't care, am I moving the data, like you said, a few inches or, a couple of kilometers? Programmer shouldn't care. The developer in PyTorch shouldn't care at all. Should look completely transparent to them that they have what's under the hood for that. So that's another piece of this. The third part is simply a belief that the speed at which these workloads evolve is actually at the speed of software, not hardware tapeouts. Mm-hmm. It means that you want to have a very smart division of labor between what happens in user programmable code versus what is hard codified into gates. Because hard codifying into gates means, okay, I need to change things. I need to tape out another chip.
Tape out again.
So you're looking at, delays that are measured in years than in minutes or days. And we fundamentally believe that there is a division of labor that you want to get between your data plane and control plane when it comes to how these workloads are built. And we've come up with an architecture that smartly places what customers need to be programmatic in programmatic resources and what needs to be hardened and fast in hardware. And that allows us to build a super NIC that is 4 times the performance of the next, highest throughput NIC that is out there today. We're even through the end of the year. We build a product that does 3.2 terabits of network throughput and 160 lanes of PCIe facing the system, compared to a dual 400 gig NIC, which is the state of the art today.
Well, that is pretty impressive. And I think you hit on a few points that are clearly what the market is telling us as well, even though we play arguably in different parts of the supply chain, right? So for us, we're moving data between compute elements on the same die. They may be diverse, maybe heterogeneous compute elements. And then we're also moving data across or helping build systems that may be packaged into the same chip, but are built out of chiplets. And so you still need to understand. So we're actually trying to work on problems that are helping people build chips faster, where the data movement is taken care of. And at least you have no surprises when you get out, with built-in kind of both telemetry and programmability for future-proofing. But I think we both kind of agree that even though different tapeouts are take a while, you can build future systems with somewhat of a Lego block approach that chiplets bring us, right? So that turnaround is a lot faster if your units are more compact and scalable. So what are your thoughts on chiplets and how they affect what we're trying to do?
Yeah, I think you're spot on with your assessment of, it's a very nuanced point. But just to go back to like striking that right balance in your product architecture and how it's built influences a lot. It influences your investment profile to go build a new product, the longevity of your asset, how long can it survive that life? You could argue that that's actually one of NVIDIA's strongest moats, is that GPU architecture. Even if they, tune the amount of the microscaling formats or, tensor cores versus traditional kind of floating point processing cores, the programmatic ability, the programmability of that architecture is what's made it applied to recommendation engines, to LLMs with transformer, to vision, to a variety of workloads. And the capability of that instruction set and what they've decided to make super performant in hardware versus software is a key to if you built by the way, a recommendation engine optimized ASIC, 5 years ago and expected to take the world by storm, your company's probably dead by now, right? So that is super important. And so whether you're doing it at the NoC level or at the chiplet level or at the monolithic chip level or at the system level, super important to be able to make those trade-offs of deciding what should be soft, what should be hard, and how much control do you give to the user to be able to design that in. It's not free. As you know, you can't build a NoC at the lowest possible power and make it programmatic, right? So there are trade-offs to be made. Now, you bring up an important point about chiplets, and I think that there's a practicality argument versus a sort of an ideation argument. I think the idea of chiplets is required, and it's where things need to go because of increasing costs of tape outs, the fact that analog scales differently than digital, so there's a reason to have to kind of split that up. Obviously, the advent of HBM means that you already have kind of like chiplet-based integration that's already proliferating. As a startup, though, I also look at it as what is the simplest way to get product into the customer's hands. And we have to look at that first and foremost. And so for us, I will probably always favor building a solution that is monolithic in nature, rather than a collection of chiplets, just because it reduces the dependencies and shortens the time to revenue, because I don't have to go through a known good die, sort of like process and then couple that to something else, get a multiplication factor on yield. Chiplets add, beachfront requirements, they add power if you could do it monolithically. Now, if you can't do it monolithically, then obviously chiplets are required and they're your answer. Or if, you're a component vendor that's building a chiplet and it only works if it works in conjunction with a larger die that it's attached to, then it's part of your business model. But where we have sort of opted in this current phase of the company is we understand the value of chiplets, and we certainly think that there are chiplet-based products that are in our maybe not so distant future. But our first incarnation of the ACF SuperNIC was basically an aggregation of all of the data to a bigger element rather than the diffusion of the functionality into smaller chiplet elements that could be added. And I'll tell you that there are different camps in terms of the belief on what is the right way to go. We do know that there are certain architectures that are out there that are choosing to say, hey, let's make the NIC a chiplet and just glue it to the accelerator and have, Ethernet or whatever scale out technology, InfiniBand, come out of, that accelerator. We think that there is definitely a lot of coupling of risk in that kind of environment in terms of just getting two odds. There may be certain arguments as to why you want to do it. I think one big one is going to be power efficiency, and that's certainly a good argument for chiplets. But, I'm interested in also getting our product to market as quickly as possible and removing all obstacles to get there.
No, understood. And I think, the thing about IP for us is we get to see different solutions, different innovations, and different challenges that are coming together, right? So if you think about, hey, can I scale? Can I actually create a multi-SKU product line based on core elements, where some of the, especially the SerDes, PHYs, et cetera, are well understood and can be reused. The compute elements or the networking elements are separated, or the acceleration elements are separated. We do see a lot of that. And of course, there is horses for courses, depending on what stage of your market entry or market scaling you are. Right? I think it's not something that is going to have an easy answer either way, but that is now almost every engagement that we've been, they will do a very strong review of whether it has to be monolithic or separated. So I think it's a a wild west, if you will, right now, which is exciting because there's a lot going on and a lot of innovation.
I think that in a matter of like a few years from now, Enfabrica's product portfolio will feature highly aggregated, dense elements that are monolithic all the way to chiplet-based offerings. And it's simply the level of scale that you need as a semiconductor vendor now to be able to address the full market.
Exactly.
But when you are small and having to, sort of break out, you really have to reduce your focus. And that's a function of where your capital investment can really go. And my advice to anybody doing this is like, be hyper-focused on your one entry point and just nail it. Because, you can do this in bigger companies, but in a small company, you can ill afford to spray your efforts and, risk weight them and figure out, well, if this doesn't work, I'll do this. Like, you'll run out of money before you settle on a strategy. So you've really got to.
No, absolutely. I think what you bring is a very clear hyper focus. Now, you mentioned a couple of things regarding NVIDIA's kind of leadership in this. And I honestly think the adoption, not just of the software-based strategy, but the fact that data movement was critical. I think the Mellanox acquisition, the NVLink development has been kind of a signature for success. And the area that I want to kind of focus on a little bit more, right? It's not just GPU. I do feel that as you're getting into these potentially verticalized segments, especially things like networking infrastructure, et cetera, you do have specialized acceleration required over and above either a CPU or a GPU, or even some kind of NPU as well. So NVLink kind of out the way, you're seeing UA Link and Ultra Ethernet coming up to kind of help that ecosystem grow. How do you see that evolving? And also, what is your view on the NVIDIA's kind of tip of the hat effectively to this kind of diversified solution with the NVLink Fusion?
Yeah, there's a lot there to unpack. So let me maybe start.
Sorry, I had a complex questions. You probably went into 3 items there.
Let's just first start with, why are these systems, sort of being built this way? So I think the first thing to recognize is, compared to conventional distributed systems where you could shard workloads very cleanly between nodes, there wasn't a whole lot of dependency. I mean, take out the HPC market for a second, which is a niche market, but for large-scale distributed systems, for the most part, you could shard the workloads pretty evenly. You could easily disaggregate components, between compute, storage, memory, network, and the like. And that's the formula for kind of cloud 1.0, right? That's how we got to very efficient scaling of cloud computing resources, is just sort of, being able to scale those dimensions independently. With AI and accelerated computing workloads, there's definitely tighter coupling between the software and hardware stacks, between that workload being spread amongst multiple parallel workers. And therefore, there's sort of like this tightly coupled domain and then a more loosely coupled domain. So what you'd explained about NVIDIA's approach was they already had NVLink. NVLink actually started as a way to connect to GPU cards, right, in the graphics world, to be able to do the rastering between, different, horizontal, vertical, and types of arrays. So that type of interconnect started well before AI, right? It emerged into what it is today based on, the usage and leverage of that interconnect for scale up. The Mellanox acquisition was purely on the scale out side for the most part, right? With respect to their NICs, InfiniBand, and Ethernet switches and the like. So really, I would say 2 different interconnect topologies and schemas. And what Enfabrica is actually trying to do is actually, like I said before, elasticize that and basically unify one domain to the other. So today we may be in the world where scale up looks very proprietary and scale out looks very different over network protocol. The way Enfabrica envisions this evolving, and what our product does today, is basically allows the free movement of data between those domains. And we see, the advent of UA Link as an open alternative for scale-up technology as being a good thing, as being something that seeks to normalize and make standard the interfaces, both hardware and software, in order to be able to scale that. Ultimately, there's a tension between how fast it takes a single vendor who can produce a system that combines all those components together and how quickly they can get that to market versus how an entire industry can make independent progress on their own systems as quickly as possible. So that's the tension that we're in right now. Should we continue building and deploying as mainframes, or should we be smart about the interfaces that we disaggregate at? My firm belief, and what is at the heart of it, Enfabrica's assumption, is that between compute resources and data movement exists a pretty clear opportunity to disaggregate, right? And to do that at the level of the system. It means that you have a scale-up domain between compute resources, and you can, move things within there, but then to be able to normalize that movement interface, it doesn't necessarily save every infrastructure vendor's time to sort of landlock a larger system, which includes all of the networking and the like. So we believe that actually different infrastructures will focus on different value propositions. We'll have ones that focus on inference of certain types of models. You might have ones that focus on training. You might have ones that focus on different types of multimodal or multi-model type of workloads. Digital twins and the like might evolve differently. So are we going to try and hammer all of that into the same 72 GPU, HBM-rich rack with a certain amount of, storage and a certain amount of networking bandwidth? It seems far too rigid a bin pack. And the way to actually, the easiest way to modify and allow people to differentiate in how optimal and efficient they can build those systems is to actually cleanly disaggregate at one particular interface, not all the way down. We don't have to disaggregate everything. There's diminishing returns in trying to do that. Mm-hmm. But at least at the level of data movement between clumps of flops and other resources and each other, I think there's definitely a room for disaggregating that, and as a result, accelerating through the availability of open interfaces, the ability for lots of infrastructure builders to deploy, accelerate time to market, and produce systems that meet customer needs faster.
I mean, it sounds about what we're saying as well, which is you are going to disaggregate, you are going to have customized solutions, and people are trying to cycle through quicker and quicker with hopefully emergent kind of more open standards that allow them to do that. Right now, we're actually enjoying this discussion and it's moving really fast, but unfortunately we might have to actually bring it to a close. But before we go, right, clearly data movement, I think, is an important piece of whatever the next generation is, right? You've been close to at all the various levels of what data movement is. What about new tech that helps it? I mean, optics and optical has already kind of factored in. Yep. What are the other boundaries? I mean, how does silicon photonics start coming in? How does optical push boundaries, or is there more?
Yeah, there's a, if I had all the answers to that, then, I guess I wouldn't be still here laboring through, trying to push through this one company and getting our product to market. But certainly you can see the electrical to optical transition happening, that there's just going to be a wall, right? Once you start going from 200 gig SerDes to 400 gig, historically all of these interfaces in the rack have been based on long reach SerDes, and there's definitely going to be, a cost curve that then and throughput curve and power that's going to favor the deployment of optics. And I think power is actually going to be the biggest thing that accelerates that. The introduction of optical engines that are closely coupled to the data movement engines, wherever they are, right? So it could be directly out of an accelerator. It could be on devices like NICs. We're already seeing them on devices like switches that are higher up in the network. But I think that's going to happen. And it's going to be a question of solving the manufacturing, the system complexity issues that go along with that, so that you have sort of reliably deployable. I think the thing to remember about optics is this is one area where it has to just be able to recover from failing, and failing at the frequency that components fail in a data center without affecting the system. That's fundamental to the deployment of technology is robustness. So while the promise is there and the clear advantage of doing that from a power and bandwidth perspective exists, it's really about reliable deployment. I think we'll see that over the next few years. I think that's definitely happening now. Beyond that, I think that we have a lot to optimize in terms of systems. Like, there is the innovation that happens at the media level, and then there's the innovation that happens in terms of the models themselves. I think it's important to notice that the DeepSeek-driven movement is not just about, sort of a China-based, kind of way of doing it cheaper. It's really sort of like a trend that could be, hey, get very good reasoning at much smaller model sizes with much more creative ways of moving data within and outside the systems.
Yep.
And we're going to see a lot of algorithmic innovation that might actually attenuate the amount of data movement that has to be done, because right now on the path it's on, it's a massive explosion.
Yep.
So there's going to be algorithmic sort of advances. There will be interconnect advances with our optics. I won't even go to the level of what quantum will bring maybe within the next 5 to 10 years. I'm certainly not an expert in that, but I can see that shift sort of, giving rise to some changes in how, what type of workloads can benefit from it. But I think ultimately data movement is key to software flexibility. And so that's going to continue for at least a decade in terms of being relevant. So that's really the level of horizon that I can see, and that we at Enfabrica can continue to build and tune our products to be able to serve better than anything else that's out there.
Well, that makes sense. And in fact, my philosophy, at least from seeing all tech through various generations, is you need different levels of innovation and efficiency, whether it's at software level, system level, data movement level. So the fact that DeepSeek can do certain things at an improved accuracy level just means now you can monetize things better. And that also means you'll get more accurate, more involved models that again put pressure back on the compute and the data movement. So it's a continuing path. But that brings this kind of fun discussion to a close. Unfortunately, we have to stop. But I really appreciate you coming in and sharing your insights, and wishing you and Enfabrica the very best. It seems like you're just ready to blast off.
Thank you, Nandan, and likewise, all the best to you and your team over at Baya. And we hope to see each other hit stride soon.
Thank you for listening to Tech Threads, Weaving the Intelligent Future podcast. Join us monthly for insights into the evolving tech landscape and the future of chiplet technology. If you enjoyed today's episode, don't forget to subscribe and share it with your network, and stay tuned for more expert discussions. Let's weave the intelligent future together.